All right, hello, Ling 441. We're back. Normally, this is the first lecture I give after the midterm, and hopefully that's still the case because that's what I've got planned for this semester. And so basically, the idea is to continue on from some of the themes we were developing in our analysis of voice quality from the last lecture, including measures of things like spectral tilt and our analysis of the Korean stops. But today we're going to talk about resonance, or at least get started on talking about resonance. But I'll add here that in the past, I used to have a whole unit devoted to understanding how to generate spectrograms using Fourier transforms or Fourier analysis in general. So this is why I have this little cartoon on here, which you can read through if you want. Hopefully you find it slightly amusing. But what you might find even more valuable to you is that I have posted those old notes on Fourier analysis as enrichment material to the course website. You can download them there. So ultimately, we're going to do, the next homework is going to involve a technique you can use to measure the length of your vocal tract. And that's going to be what this lecture and the next lecture are kind of leading up to, or that they eventually develop your ability to do. And in addition to that, if you want to read those extra notes on Fourier analysis, how to do that from the bottom up, you can. And then there's going to be an extra credit assignment on that homework, which you can try your hand at by applying Fourier analysis to a couple of mystery waves, sort of like what we did with the automatic pitch tracking exercise back at the beginning of the semester. So that's not a complete wash there. You would not only get some more knowledge out of reading those notes, but you might also get some more points for your course grade if you want to check them out. But the reason I don't go through them anymore is because they involve a lot of detail work, which is kind of hard to present in class, and it's kind of really difficult to present in a format like this. Anyways, so you can look through it if you want. You can ask me questions about it if you want, and then there will be an assignment based on that in the future that you may or may not, or you can choose whether or not you would like to do. Okay, so like I said, today we're going to talk about resonance. So that's basically going to give us an understanding where formants come from, which we've talked about in 341, but it's always useful to go back and review this because it's complicated. And then also we want to figure out why formants take the specific frequency values that they do, which is something we did not talk about in 341. So we're going to kind of build on our earlier knowledge in this class with these lecture notes. So also, like I said, since this is usually the lecture I give right after the midterm, people are not always in the best of moods. We'll see if that's any different this semester because I think the midterm is going to take a slightly different form, but who knows. If you're not in a great mood, or even if you are in a great mood, I have some videos of dogs and cats talking, which are at least mildly related to what we're going to do. So let's watch those. And normally I take a vote as to which one you want to watch first, dogs or the cats, and usually people pick dogs. Or at least I pick dogs. So we're going to watch this one first. These, I think, are from America's Funniest Home Videos. We'll see if this winds up being a copyright violation on YouTube. Who knows? Anyways, we're just going to watch it for fun. And if I can't post them to YouTube, I'll just send you links somewhere, I guess. Anyways, what are these dogs doing? Yeah, so it kind of helps there with the last cat. To get subtitles, I think. Also, kind of the context helps a lot too. People might be expecting a dog to say, if they want him to say "I love you" or "Mama" or whatever, then it's easier to hear that. And if you just played that out of the blue, I don't know if you get the same thing. But the point is, if there is a point, that these dogs and cats are taking advantage of resonance in their own vocal tracts to make sounds that sound a little bit like human speech. So we want to figure out how they can do that, or really more crucially, how human beings do it, and then assume that dogs and cats are doing something similar to bridge the species gap. Okay, so I will say a few notes in this lecture about Fourier analysis because I kind of want to give you a sense of how it feeds into our understanding of using spectrograms to analyze formants and the acoustic structure of speech. And these will also give you some basic tips about how to sort of tweak the settings for spectrograms in prod if you want to. So like I said, these are just part of that other kind of extra credit set of slides that I'm posting. Yeah, and just so you know, I don't think I showed you this link. Yeah, if you go to the notes on the web page down at the bottom here, there's another set of notes called Spectral Analysis. So you can read those if you want. The way they start out is by talking about how to generate spectrograms from a waveform. And the first step in doing that is to window the signal. So you might remember that the guy who figured out how to generate, well, things like spectrograms was this guy, Fourier. That's where this name comes from. So normally we do this through a Fourier transform, or sometimes we do it through a fast Fourier transform, which goes more quickly and is also more efficient for computers to use. And the first step that they apply is to window the signal, similar to the way we did this when we were looking at automatic pitch tracking. You basically break up the entire waveform into a series of smaller analyzable chunks, so you don't have to do the whole thing all at once. And also, because we know what's really one of the really important features of speech, kind of the feature of speech which makes it basically sound speechy, is that the spectral properties of the signal will change over time. And by that I mean the frequency and the intensity of the components of the complex wave change over time. When the dogs and cats were speaking, they were making those spectral properties of their sounds change over time in a way that made it sound similar to human speech. But basically, if you get that in an acoustic signal, it's going to sound kind of speechy to you no matter what. So we have to be able to figure out how those components change over time if we want to have any clue at understanding what's going on in speech, if we want to have any hope of understanding what people are listening for in speech. So we're going to start by taking, say, one window. We did this, if you watched the video on the Korean stops homework, you do this when you get a spectral slice to try to figure out what the spectral tilt is for different stop types in Korean. And we did it by sort of zooming in and grabbing like 5 or 6 cycles of the waveform. Again, like with automatic pitch tracking, a computer's not going to know exactly where one cycle begins and ends. That's the whole point of even doing the exercise of Fourier analysis, is to figure out where those cycles begin and end. So instead, it's going to take a preset sort of length of time and just kind of go through in slices all the way through the waveform until it gets to the end. So this is a setting you can actually change, and you get different information if you do change it in Prot. So I'll show you. We're going to go back to this example wave file that we had for the Korean speaker. Maybe I'll zoom in a little bit. This is not for the Korean speaker, but for the Korean homework exercise. So if you go to Spectrum and look at spectrogram settings, it will tell you what the default window length is for doing this sort of analysis. And the default length is 0.005 or 5 milliseconds. So I'll change that as we go through these lecture notes, so you can see what effect that has on what you see in here. If you change the window length, it's not going to change the sound file, the underlying sound file that you're analyzing. It's going to change what the spectrogram looks like. But basically what that is saying is that you're grabbing really small chunks of this thing. So about 5 milliseconds. Maybe I'll zoom in more. So yeah, we'll just do it for this first vowel. So 5 milliseconds, like about that long, and then we're going to analyze that, and then you're going to grab like maybe the next 5 milliseconds like that, so on and so forth, just walking through the wave file as we go. And then for each one, you're going to say, well, I want to look at, because it's a little too long, it's 6 milliseconds, about the same. You're just going to say, well, I'm going to analyze this little snippet of a waveform, and I want to figure out what are the sine wave components of this complex wave. So this doesn't look like anything we've really seen before or talked about yet in this class. We can see there's this kind of big loopy wave. So there's something kind of nice and low frequency happening there. And then there's all these little tiny bumps, which are high frequency components. But basically the Fourier analysis is a mathematical method to specify exactly what it thinks is in there and what is not. So this slide gives you another representation of that. So for complex wave extracted from each window, Fourier analysis determines the frequency and intensity of the sine wave components of that wave, the harmonics of that wave, right? So let's say I wind up, if we go back to this window here, that looks like this, the part of the sound file that we created a spectral slice for when we were doing the Korean stops homework. If we look at that close up, it winds up being this little creature here. So the idea is to take that and get a spectral slice out of it. And we already did that for the Korean stops homework as an example. So we saw that these were the component harmonics of the complex wave. My computer's overheating here for some reason. Anyways, these are the component harmonics of that little snippet of the waveform. But we're going to do that a lot. This says 1,000 times a second. Okay, so like moving every 5 milliseconds through the waveform. And for each one, you get a spectrum like this, and then you turn it on its head. So you're looking at this. Let's say my fingers are like the harmonics in my spectrum. And to get a spectrogram, what I do is I turn it on its head so that more intensity means more grayness or dark shadowing in the spectrogram, pointing out at you through the Z dimension of the spectrogram. So that spectrum just winds up being one point in time in the spectrogram, and then I move a little bit further down, I get another, something like this, and then I look at that as the next step in the spectrogram, so on and so forth, and I move down the next way, and I get one, and that's my little point in the spectrogram. So I got to create a lot of different power spectra going through the entire waveform, and then that's going to change how the component frequencies look, or it's going to show you how the component frequencies change over time in the sound file itself. And that's how you get a spectrogram. That's the basic idea. Okay, so what would happen, just so you know that there are problems with doing this that you have to consider, or at least the engineers have to worry about. So let's say we windowed a waveform like this. This is something I encouraged you not to do when you're doing the Korean stops homework, because what you wind up doing if you're not grabbing we're at the so-called zero crossings of the waveform itself, or necessarily grabbing a complete cycle of this complex wave, is that you wind up getting a waveform that doesn't start or end at zero. So you get this particular chunk here. So we can see this nice loopy complex pattern repeating about 3 times, maybe 3.5 here. But what I want to do when I'm doing a Fourier analysis is this is what I've got as a computer. I don't see anything else, so I'm just like, well, what sort of combination of harmonics, what sort of combination of sine waves can I put together to get this particular complex waveform? And this may not be immediately obvious, but when you have the waveform cut off here at the edges of this chunk, then this goes basically from 0 to something, 0.8, or from negative 0.6 to 0 instantaneously. So normally we're getting a smoothly changing waveform here with some little bumps here and there, but when we get to the beginning and the end, it's just a dramatic change going to 0, either into or out of the waveform, right? You might recall, I told you at some point that when you get rapid little changes in the waveform, that's a sign that you've got high frequency information somewhere, high frequency components somewhere in the complex wave. So the computer, again, doesn't know that because the computer's stupid. It's just capable of repeating instructions very quickly and indefinitely long. So it does this grunt work for us, but it can't see that this is what's happening. We can kind of figure it out as human beings, but we just don't have to want to worry about it. So what the computer sees is just a rapid change. And when it sees that rapid change to almost the peak amplitude of the complex wave, it has to assume that there are a lot of high frequency components basically in the complex wave. So it's going to give us it's going to think that there are a lot of sine wave components in the signal which are not actually in the signal and instead are just an artifact of the way that we splice this. We don't want the way that we splice this to create artificial harmonics in our Fourier analysis. We only want what's legitimately in there. So normally what you do is you reduce the amplitude of the waveform at the edges of the window that you're looking at by transforming that particular snippet of the complex wave with what's called a smoothing function before you do any of this Fourier analysis. So this is kind of interesting because you actually have choices in how you do this. So this is, say, your underlying complex wave here, bouncing up and down, sort of like the one we just saw on the previous slide. And then you apply this so-called smoothing function to it. And all the smoothing functions we'll look at least all the ones that you might want to use, have some sort of peak in the middle of the window, and then they kind of go down relatively smoothly, or what did it say, monotonically, to the edges where they reach zero at the very edge. So what you do is you basically multiply the amplitude values of the complex wave by whatever the smoothing function is at that particular point in time. So in the middle, it'll look basically the same as it does in the original, but then the amplitude kind of gets smoothly decreased towards the edges, sedulously decreased towards the edges until it finally reaches zero no matter what at the very edge of the window. And that prevents any sort of artifacts from entering into the analysis due to the way you just spliced it at the edges. This particular smoothing function is known as a Hanning window. There's two window I'll show you a few examples here. There's two different window names which sound very similar. There's one that's called a Hamming window and one that's called a Hanning window. This is the Hamming window. So this one doesn't go quite down to zero at the edges. It looks like a parabola, and then there's a little bit of arms on both sides, I guess you might say. So I think the story is the Hamming window was named after Mr. Hamming, and then Mr. Han developed this window, and they're like, well, we already have the Hamming window, so why don't we just call Mr. Han's window the Hanning window, because that won't be confusing. I don't know. Anyways, if you want a triangular window function, it's called a Bartlett function because apparently Mr. Bartlett invented the triangle. But anyways, like I said, it goes to basically a vertical representation in the middle, so it's multiplying the whole waveform by 1, and then it just kind of smoothly, in some sense, linearly goes down to 0 on the edges. This is the Gaussian window, named after Mr. Gauss, is probably the most famous of these guys. But this looks like a normal distribution, or that bell curve. Very similar to this, but slightly different math, I guess. And this is the Hanning window, which is nice because it actually does go down to 0. And then this is a Welch window, which is, I guess Mr. Welch, invented the parabola. But there's also a rectangular window. I got all these off. I spent an afternoon on Wikipedia once, and you can go find. There's even more of them over there. This is a rectangular window, which is just a window that doesn't do anything for you. So this is basically the same function, just multiplies everything by 1 across the board. So it's like not windowing the signal. And we can look at that to get a sense of how that messes things up. So let's go to this waveform. Okay. So this is another setting you can change. Let's listen to this again.
촛불.
Yeah, I think we all remember what that sounds like. So we can go to the advanced spectrogram settings. And here are our options. They're the ones we just talked about, right? So Hanning window is the first. So my default is Gaussian. I feel like it just looks the best. And if we change this to some of the similar shapes, so like Hanning was almost the same shape as Gaussian, the spectrogram is not going to change a whole lot. Like if you look at that, you see a subtle little shift in the frequencies. Oop. Yeah, but it's not much. And then we can also look at, say, the Hamming window. And we're starting to get some weirdness here up at the top.
촛불.
Exact same sound file, but this spectrogram looks a bit messy, right? Not sure if we want that. We can look at some of these others. Let's look at the triangular one. Yeah, maybe that one's a little better.
촛불.
But basically the same information. And then we can also look at the parabolic window.
촛불.
And we get some of that weird, like fuzzy stuff at the top. Where we're really going to see a difference is in a rectangular window, which is not doing this windowing step at all. And all of a sudden,
젖불,
this is not what we want to see, right? You can kind of see some of the formants in here. I'll remove the pitch. You can kind of see some of these formants like ghosts in the machine. But
뿔,
this is bad because, you can't really
젖,
measure anything in that. Like, you get some timing information. Well, there's my initial stop and affrication, but
뿔,
I don't want to do anything with this. So let's go back to the Gaussian window and just appreciate the value of the fact that this is kind of the default setting that Prog gives us,
젖불,
and it makes our lives a lot better for that reason. Okay, so we window the signal, then you do your Fourier analysis where each step you figure out what's the intensity and frequency of each sine wave component of the complex wave to the best of your ability. There's a little bit of fudging it that you have to do, but basically you can figure it out. And again, read those other notes if you want to find out the magic, how the magic works. But I'll jump to the end of the story here and tell you that shorter analysis windows, like the default setting for a window length in PROT, will give you a better temporal resolution and worse frequency resolution. And the name for these things is that they're called wideband spectrograms. We can contrast those with what are called narrowband spectrograms. And the difference, basically the only difference between these two is that narrowband spectrograms are generated by longer analysis windows. And usually the default setting I use for that is 0.03 seconds or 30 milliseconds for a window length. If you do that, and I'll show you what happens when we do that in a second, you get better frequency resolution, but worse temporal resolution. So let me jump back and forth here a little bit. So I'm going to change my spectrogram settings. All I'm going to do is change the window length to 0.03. And it looks very different, right?
젖불,
Same sound file, but all of a sudden I am seeing the harmonics here way better than I could before. I'm not really seeing the formants very well, but I see the harmonics quite nicely, and this ties into what I just said here. When you have a narrowband spectrogram, you get better frequency resolution. So you can pin down better where exactly in the frequency scale those harmonics are, but timing is more messed up. And hopefully, like, you can walk through those notes again, but hopefully it makes sense when I say that, because if my window length is longer, that means I'm incorporating more of the underlying wave in a longer window, and I have to figure out everything that's going on in that particular stretch of time. If I make that window shorter, I just get better time resolution because I'm looking at a smaller length of time. I'm figuring out what's happening at this moment and then what's happening at this moment. In fact, because the narrowband window is 6 times as long as the wideband window, you kind of get like 6 times better temporal precision with a wideband spectrogram than you do with a narrowband spectrogram. So once I do that, I can see things like glottal pulses. So I can see every individual opening and closing of the vocal folds here, which I could not see before looking at that narrowband spectrogram. I can't see the harmonics in this one, but how much do I care about the harmonics? Not that much. Here I can't see the glottal pulses. I can see where the harmonics are. I can see generally where the formants are going through them. But if I really want to see the formants well, I'd rather look at a wideband spectrogram. And then I can kind of get a sense of what's going on with glottal pulsing, because that's a source feature of speech. That's telling me what the vocal folds are doing throughout. So I don't really need to see the harmonics unless for some weird reason I want to take a look at them. So this is kind of our default for that. If you look at a shorter amount of time, you can't analyze as many different frequencies in that short amount of time because some frequencies just take longer to kind of go through their cycles. You can see those frequencies better if you look at the longer window, the narrowband spectrogram, but then you're looking at a larger chunk of time and you don't get that precision on the time dimension that you might want. So there's a trade-off between the two. And then I've also got this note here that if you do not smooth the window or the windows you're looking at, you're going to get a really messy spectrogram. So don't do that. And you will know right away you don't want to do that if you have any feeling of comfortability or being comfortable with what spectrograms look like anyways. Okay, so that's the morals of the other set of slides. If you want to work out how the nuts and bolts, figure out how the nuts and bolts of this process work, go look at that, and that will sort of get rid of some of the mystery behind why we have this sort of trade-off between the two types of windows. now I want to talk a little bit about this terminology. So like, why are we talking about wideband or narrowband wideband or narrowband spectrograms? And it goes back to kind of the history of how these spectrograms were first generated back in the 40s and 50s, where they were kind of relying on a system of filters to get the spectral information out of the waveform. So if you can remember, way back at the start of the semester, we talked about different kinds of filters, like low-pass filters. So a low-pass filter is one that allows harmonic components or sine wave components of a signal below a certain frequency to pass through our analysis we did, or whatever we're filtering. And we generated a few examples of how to filter a sound file in prot, so you just get kind of a low frequency information. This is an example of a low pass filter that filters anything below 250 hertz. So the output would include this particular sine wave component, but it would remove this one. So it gives you that kind of muffled sound, right? It's just the low frequency stuff. And then there's also high pass filters, like let's say we created a filter that just filtered out everything below 250 hertz, then we'd only get this component in this particular complex wave. So you get the high pitched information without sort of the underlying stuff. Like a high pass filter that removed everything below 250 hertz would pretty effectively remove, say, all of the F0 from my voice, and you just get basically the formant information instead. So you can do that. People do play around with that sort of technique for various speech perception experiments for different reasons. I'm not going to get into that right now, but there are sort of practical applications of these. And there's also a third kind of filter, which is called a band pass filter, that combines both features of the high and low pass filters. So it basically passes a band of frequencies around a center frequency. So this one is centered around maybe 700, 800 hertz, something like that. So it's going to look like, well, a parabola or maybe that Hanning window or one of those other kinds of windows. But it's applying this to basically the spectrum rather than the waveform. So any component frequency of the complex wave within this lighter window will go make it through to the output of the filtering process. Anything around this will not make it. And then there's also, so there's a couple things here. It's going to sort of multiply the underlying intensity of the component frequencies by the shape of this window. So if there was a component frequency right in the middle of this one, let's say it's 800, that would come through at its full intensity. But if it was sort of over here, then that harmonic at about 1200 hertz would only come through at like half of its intensity overall. So that kind of leads you into this other concept of bandwidth, which I define on, I'll get to bandwidth in a second. This shows you what I was just talking to you about. Let's say we had just a series of harmonics here. I don't know how many, this is maybe 10. So they're at each 100 hertz underlyingly, and they're all the same intensity. If we apply this band pass filter to them, this one's centered at 600, then we'll get this nice sort of band pass filtered shape of the output spectrum, such that the ones in the middle are coming through at their original intensity, but this one over here matches up to this point on the filter. So this whole thing gets cut down to size to match up the shape of the filter. And we can see when we do this, sort of the underlying series of harmonics from this spectrum here, and we can also see the shape of the filter too, kind of overlaid on top of that series of harmonics. So the components of the input spectrum have to conform to the shape of the bandpass filter. That's what we're doing here. I'll actually give you one example with our well-known sound file now. If you filter in prot, the default gives you a bandpass filter. It's called filter pass handband. So there's Mr. Han again. I got that story right, apparently. So the default is to filter with a bandpass filter from 500 hertz on the low end to 1,000 hertz on the high end. We'll just apply that to this particular token and see what happens. Look at that. So this should be centered around 750 hertz, more or less. And the top edge of this should be about 1,000 with some, bleed over the edges. And what it sounds like is Yeah, let's try that again. Yeah, so we're losing a lot of information in there, right? Same sound file originally as this,
촛불,
but you only get this part of it. Yeah, so that's a band pass filter. It's giving us a range of frequencies from the original signal. And this too mentions this concept of bandwidth. So the bandwidth here is 200 hertz. It goes from 500 hertz on the low end to 700 hertz on the high end. What is bandwidth? This is a term that people throw around with the internet. Once I had a student ask about that connection, and it turns out there's really no connection at all. It's just sort of like an artifact of history that they borrowed this word from electrical engineering and applied it to the internet. So don't worry about that. For our purposes, bandwidth is the range of frequencies over which a filter responds at 0.707 of its maximum output. So let's say in this particular example, we had a sine wave component at 700 hertz. And this is the point at which you'd be multiplying whatever its original intensity is by 0.707. This might be a kind of funny number to you. It turns out it's actually the square root of 2 over 2. Or if you think about that in a different way, it's the square root of 1/2. And if you recall from 341, this isn't crucial, but our definition of acoustic power was the square of the waveform, basically, the square of the intensity. So you're basically looking for the spots where you get half of the acoustic energy passed through the filter. That will fit within the bandwidth. Yeah, so that's why it's the square root of 1/2, is you're trying to get half of the power of the original waveform through this filter. And whatever range is defined by the bandwidth is what gets you that. Bandwidth is measured in hertz. Again, this is not super crucial information to know, but that's just what these terms are referring to. It's also going to help us understand why we have this terminological difference between wideband and narrowband spectrograms. So a wideband spectrogram, as you might imagine, has a wider bandwidth. So this one is centered around 450 hertz, and its bandwidth is from 350 to 550. So it has a bandwidth of 200 hertz. This is a very narrow band filter. So this one is centered around 100 hertz, and its bandwidth is only 10 hertz, right? So it's a lot narrower range of frequencies they're going to be able to pass through that band pass filter. And I will show you one other thing you can do in Prot, just for kicks. Let's say I turn on Formants here. So this is doing a pretty good job. It's a nice clean recording.
촛불,
Maybe it doesn't need to be that loud, but it's doing a good job of kind of spotting where the formants are in this thing. That doesn't always happen with Prot. But let's say, I think I need to grab that spot. Yeah, so if you look at under Formants, beyond like just the show Formants, this gives you the option for getting a lot of different kinds of information about this formants. Like, what does it think the first formant is? It thinks it's about 419.8 something. Down here. Yeah, close enough. And then it will also tell you what it thinks the bandwidth of that first formant is. And that says it's about 28 hertz. Usually as you go up the scale, the higher formants have wider bandwidths. I'm not entirely sure what the reason for that is, but if you want, you can actually click on Get Formant Listing, and it'll tell you what all the formant values are for a particular spot in time. And yeah, so I think this is for, I don't even know if there is a formant here. Anyways, I thought there was a way to get all the bandwidths at once, but I guess there's not. You just can grab them kind of individually if you want. And like I said, they tend to get bigger as you go up the scale. Yeah. So that's what I'm going to say about that. But the reason I'm talking about it is because of how they used to generate spectrograms back in the old days. So I never used one of these, so I'm just going to go off legend here. But the idea is that you had a microphone that was collecting sound from some speaker somewhere in the room. And then you would link up that microphone to a series of band pass filters, each of which was tuned to a different center frequency. And what I believe was the case was that they all were supposed to have the same sort of bandwidth, so that they can kind of like line up in a range of frequencies from 0 all the way up to the top of whatever you're looking at. So you collect the sound from the microphone, and it would create like some sort of electrical waveform in the circuitry here. And then this band pass filter was dedicated to sort of analyzing frequencies of a particular range, from like 0 to 100, say. This one would be from like 100 to 200, so on and so forth, all the way up the scale. And then each one of those filters was hooked up to a little light, which would shine light of varying intensities based on how much voltage was coming through these filters to it, based on whether or not those frequencies were in the original signal or not. So we'd have like our 0 to 100 hertz light, or 100 to 200 hertz light, so on and so forth, all the way up the scale. And then you'd have this moving sheet of carbon paper twirling around at a very rapid speed. And then as it would go through the machine, these lights would shine on it and kind of burn a carbon streak in the paper according to whether there was intensity at those frequency ranges or not. And that, my friends, is why all of our spectrograms to this day, or almost all of them, look like smudgy carbon paper, which is a technology you, being as young as you are, probably never even got to use. But
촛불,
if there's more intensity at a particular spot, you get darker smudges, right? And if there's less, you get less smudginess. But the fun part of this is that you could tweak the frequency ranges of the various bandpass filters. So if you wanted to make them wide, like say the first one was supposed to be from like 0 to 250, then 250 to 500, something like that, you would get a wide band spectrogram, which looks like the wide band spectrograms in Prot. Or you could tweak the ranges to be narrower than that, like say this one is 0 to 50, 50 to 100, so on and so forth. That's where that terminology comes from, and the output, the results of changing those settings is the same, right? The narrow band spectrograms look like they have better frequency resolution. The wide band spectrograms look like they have better time resolution. Okay, I've got a couple of examples here. I don't know how helpful these are, but going back to like our source features of different voice qualities, this is a modal voicing EGG waveform, and if you crank out a narrow band spectrogram of this little snippet, it winds up looking like this. So these are kind of the harmonics you get if you're just thinking about somebody voicing without worrying about their head being on top of their neck, or the voicing having to go through the vocal tract to get out into the world. So you just get a series of harmonics that are equally spaced from each other, and generally speaking, they're going to decrease in intensity as you go up the scale. With a narrow band spectrogram, you can see those harmonics quite nicely because you get good frequency resolution through that form of analysis. This is a tense voicing waveform. This is the snippet I showed you in the previous sets of slides. And then we get a similar analysis here, what looks similar when we do create a narrow band spectrogram out of these guys. And that you're getting these evenly spaced harmonics all the way up the scale, and they're supposed to decrease in intensity. But because this is tense voicing, we have less spectral tilt, so they don't decrease in intensity quite as rapidly as what we get from modal voice. Yeah, that goes on for quite a while. All right, so anyways, with spectral tilt, the idea is that it's not going to decrease as much, at least from H1 to H2, the first harmonic to the second harmonic, as for modal voicing. So this is a bigger leap for modal voice than what we get for tense voice. And you can kind of see that in the narrow band spectrogram, but usually it's better just like create one of these power spectra for whatever you're now analyzing, and just calculate the numbers specifically for spectral tilt for these different types of voicing. Okay, so I gave you a whole lecture about that, so I'm not going to belabor it any further. But the idea is that you can kind of look, with an EGG, you can look at what's going on here independently of what's going on with the rest of your vocal tract. But we can't do that with normal acoustic recordings of speech. So when we look at this one, we saw this in the last lecture when I was walking you through how to do the Korean stops homework.
촛불,
This is the same old sound file again, and we looked at the first sort of snippet of the vowel in the second half of the statement here,
촛불,
and we got this spectrum out of it. So this is funny because I've been telling you all along that normally what we get for the complex wave coming through your vocal folds is a series of harmonics which are evenly spaced in terms of frequency, but in intensity they tend to consistently go down as you go up the frequency scale. But this one is a troublemaker because it goes up. So we start with H1 at this intensity level, and then it goes up to this. So we're actually getting negative spectral tilt, which is weird. And I talked about that a little bit with the Korean Stops homework video, but why is that? Why is it going up, not down? Think about that for a second. I'm going to take a break and end this video now, and then I'll give you an answer when I return.